Hey guys, welcome to 5.3b. This video is going to be about solving some more complex trig equations and is made to immediately follow the video Solving Trig Equations Part 1. The types of equations that we're going to look at today look like the two examples I put at the bottom of the slide. 2 sine squared of x minus sine of x minus 1 equals 0. That looks an awful lot like a quadratic function. If I replace sine of x with, I don't know, z, I might have 2z squared minus z minus 1. And we know how to deal with that. Today we're going to deal with that as a sine function. The second one would be 2 sine squared of x plus 3 cosine of x minus 3 equals 0. Here we have two different trig functions. We're probably going to end up converting them using some identities into the same function. To solve these equations, we're going to use the same principles that we used in our last lecture. We're going to use our algebraic techniques, collecting terms on one side of the equation, factoring when appropriate, using trigonometric identities to try to get everything into the same trigonometric function if possible, and isolating single trig functions to use the inverses to solve. Let's take a look at our first example. In fact, this is the example you saw on the first slide today. 2 sine squared of x minus sine of x minus 1 equals 0. This is really a quadratic form of a trigonometric function. And what we can do is factor this. If I imagine this as 2z squared minus z minus 1 equals 0, well, I know I could factor that into 2z plus 1 and z minus 1. If you have trouble because there's a coefficient other than 1 for the squared term, think about the fact that 2 is a prime number. It's only going to have factors of 2 and 1. Once you get those in place, you can try other values for the second term in each binomial and come to a solution pretty quickly. So this could factor into 2z plus 1 times z minus 1. In terms of sine, we have 2 sine x plus 1 times the quantity of sine x minus 1 equals 0. From here, the equation gets a little bit easier. We're going to take a look at each of our terms and find some solutions for those. Start on the left with 2 sine of x plus 1 equals 0. I'm going to isolate my sine of x, subtract 1 from both sides, divide by 2, and I get sine of x equals negative a half. Take the inverse sine of both sides, and I get two solutions between 0 and 2 pi. 7 pi over 6 and 11 pi over 6. For the right term, sine of x minus 1 equals 0, I have sine of x equals 1 after adding 1 to both sides. Take the inverse sine of both sides, and I arrive at x equals pi over 2. You notice that this time you weren't asked to find x in a certain interval. What that means is we need these general solutions. Remember that the period of sine and cosine is 2 pi, so we need terms that are plus 2 times n times pi. For our 7 pi over 6, we arrive at 7 pi over 6 plus 2n pi. 11 pi over 6, we're going to add our 2n pi to also. And pi over 2, we're going to add 2n pi also. Example 2, which is the second example from the first slide. 2 sine squared of x plus 3 cosine of x minus 3 equals 0 for 0 to 2 pi. This time we are using an interval, and I used interval notation for that. Please remember that the square bracket means inclusive, so this would be a less than or equal to sign, and the parentheses bracket means non-inclusive. That means we're not looking for 2 pi as a possible solution. Since we have both a sine squared and a cosine of x, I'd like to rewrite them both as the same function. I know how to get sine squared to cosine. I don't have a good way to get cosine to sine if it's not squared. So let's start off by converting sine squared of x into 1 minus cosine squared of x. The equation now reads 2 times the quantity of 1 minus cosine squared of x plus 3 times the cosine squared times cosine x minus 3 equals 0. Let's distribute this out and rearrange our terms to get negative 2 cosine squared of x plus 3 cosine of x minus 1 equals 0. I'm going to multiply the entire equation times a negative 1 to make this negative 2 positive, and it's going to make us a nice quadratic term to factor. So we have 2 cosine squared of x minus, the plus goes to the minus, 3 cosine x minus goes to plus 1 equals 0. When I factor this, I'm left with 2 cosine of x minus 1 times the quantity of cosine of x minus 1 equals 0. And now it's all over but the multiplying. I was trying to be funny there, it didn't really work out so well. We have our two terms, one of which must equal 0, and both of which will provide us with a solution to our equation. 2 cosine of x minus 1 equals 0. If I isolate cosine of x by adding 1 dividing by 2, I get cosine of x equals a half. There are two solutions to this. X equals pi over 3 and x equals 5 pi over 3, both of which are between 0 and 2 pi. So there are two of our solutions. Third solution is going to come from the right side. Cosine of x minus 1 equals 0. If I isolate cosine of x equals 1. This would happen at 0 or 2 pi. Because our interval includes 0 but not 2 pi, I only care about the x equals 0. Those are our three solutions. Our third example is going to involve a second set of dividing after we do the inverse, and we'll take a look at that right now. This one asks us to solve for t in 2 cosine of 3 times t minus 1 equals 0 for the interval from 0 to 2 pi. Okay, let's start out by isolating our trigonometric function, trying to get this cosine of 3t by itself. Add 1 to both sides, divide by 2. Cosine of 3t equals a half. If I take the inverse cosine, the arc cosine of both sides, I end up with 3t equals pi over 3, and 3t equals 5 pi over 3. To isolate my t, I need to divide each equation by 3. 3t divided by 3, my 3's cancel to 1. Pi over 3 divided by 3. Note that's the same thing as saying pi over 3 times a third, which will give us 1/9. So pi over 9. And we have 3t over 3, cancels to 1. 5 pi over 3 divided by 3 is the same thing as 5 pi over 9. My two solutions are going to be pi over 9 and 5 pi over 9 between 0 and 2 pi.